All right, so we want to think back to our LOLs, and we want to think about using work as part of this, okay? And I know you might not want to draw these, but they're so important and they're so super helpful. You really need to sketch them out, okay? All right, so let's look at a couple things. So if I'm pushing a box on a frictionless surface, all right, let's say it starts from rest, okay? It's just on a horizontal surface. There's no springs or anything, okay? So I'm going to have the box, the ground, even though if I'm frictionless, doesn't really matter. And I'm going to put the earth into the system. Okay, so if, say, the box starts at rest and then I apply a force to it, eventually it's going to get some amount of kinetic energy. Okay, no friction, so no E-therm. All right, so that has to come from somewhere, right? I can't just all of a sudden miraculously get energy. It comes from the work that I have done, okay, by person. All right, I have applied that force. All right, and since the force and the displacement are going to be in the same direction, that's a positive work, which is energy into the system, All right, so when I'm doing this, right, I would be always trying to think like initial energy plus or minus work equals final. So in this case, I don't have anything initially. I only have that work added. That's going to be the kinetic energy that comes out on the other side. Okay, because I didn't have anything there. Okay, and then work here, this would just be force times displacement, and then, 1/2 mv squared, but that would be the final because the initial was 0. Okay, right, so that's assuming, right, I'm keeping the person outside of the system, right, which is almost always what you do. All right, okay, and this one, let's treat friction as thermal energy, right? So we would say box, ground, earth, whatever, okay? Now this looks like this is a box that's already moving and slowing down under friction, all right? So it's gonna have some kinetic energy to start with, none of this, okay? And if I'm treating it like thermal energy, right, I would think of it as being like the ground sort of included in that, all right? So that means this whole entire system is getting a little bit hotter. So eventually if it came to a stop, what I would say is that the kinetic energy equals the change in thermal energy, okay? And I would write it like that because I would be treating it like an energy because it's internal to the system, okay? So if it's something that's internal to the system, we're going to count it as energy and not work, right? Work has to come from outside the system, okay? In the second example, I want to have the same thing, but I'm going to treat it like an outside force, all right? So I'm going to, I guess, not put the ground in the system. This is slightly confusing, but... right, I'm just going to look at the box itself, okay, and the earth, actually, it doesn't even matter because whatever. Okay, so it's going to have kinetic energy to start with, okay, but if the ground is not part of the system, then I wouldn't really say that the thermal energy is being stored in the ground, and the box is getting a little hotter too, so it gets a little tricky there, but instead of saying that, I would say that energy is coming out of the system, okay, work done by the friction force. Okay, and I would call that work, all right? So in that case, I would say kinetic energy minus work equals 0, right? Because my initial plus or minus this equals the final, or what I would really do is I would say the kinetic energy equals the work done by friction, all right? In which case that would be force of friction times the displacement, and then I'd have, my 1/2 mv squared, okay? This is almost always how you're going to do it. So even if you want to think of E-therm, even though it's not exactly the same thing, if you want to think of it and you want to draw it like this, but then still write E-therm as this friction times X, that's fine too. Okay, because that's almost always kind of how it's going to come, all right? It just depends on how you're looking at it, but mathematically, see whether you call it E-therm or work done by friction out, right, then it doesn't really make a difference, all right? Okay, now this one's a little bit, oh, this one's not confusing. Uh-oh, why is this on here? This shouldn't be on here. I don't know what happened to that. Okay, both pushing force and friction. Okay, so if I'm going to have that, right, so then I would have it's already moving. Okay, and then if I have, let's see, box and earth, all right, this force here is going to be adding energy in the system. So work, I'll just call it a force, I guess, because who knows what it is. Okay, work done by force. And then I also have the friction is trying to take out some energy. Okay, so let's say that it's an even exchange, right? Let's say if these are even, right, then the net result would be my kinetic energy would stay the same, right? Because whatever energy I'm gaining by pulling it, I'm losing because of friction. Okay, if I pull harder, right, like let's say this force is bigger, which it looks in this picture, right? I might have like an added force here because that force is bigger, which means that overall my kinetic energy is going to get bigger, right? Because that force is going to be bigger. I'm going to do more work with that force than the friction's doing, so it's going to sort of come out in the wash, right? And then I'm going to end up with one extra there, okay? And again, instead of this work by friction, if you wanted to instead draw that as E therm, that's fine. It's the same difference. It doesn't really matter. Okay, so mathematically, right, I would say like kinetic energy plus work done by the force minus work done by the friction equals the final kinetic energy. Okay, so this here is what we would call the net work, right? Because you could just, instead of going through all this rigmarole, you could just figure out what the net force is and then do that times the displacement, right? But that's effect what you're doing here, okay? Right, and then here you can see, we'll talk about this a little later, which I don't love, but basically what you're doing here is you're saying this net work done, okay, and then if I subtract this kinetic energy off both sides is the change in the kinetic energy, right, which totally makes sense, right? I'm going to get one extra box out because I had one extra box of net work, okay? All right, let's stop that one, I think.